Okay, oops, forgot my. There we go. So let me get this. It should be on. Okay, so we should be. So I sent out an email yesterday, or for those of you who are online, of course, you didn't know what was happening. So I was doing an experiment because with Zoom, when you're recording a Zoom session, it really eats through your battery. And I know that, so I always bring my power adapter with me, but I thought, no, I'm feeling risky. So let's see what happens without it. And we almost made it. We were 4 minutes short on the battery. So it's pretty bad. Can't even make 75 minutes on a full battery. Anyway, so this is what we were discussing last time. Oh, I didn't plug in the HDMI. I always forget to do that. So we were reviewing linear algebra last time. And so we'll pick up where we left off with that, which you'll see right here. All right, so we had done definitions. Basically, definitions were what is a vector, what is a matrix, talked about identity matrices, we talked about transpose of a matrix, inverse of a matrix. Then we started looking at algebraic operations before we were rudely interrupted by my lame battery. So we looked at addition of matrices, which is just element by element. You just add them together to get the new matrix. Same thing with vectors. So u plus v, just add the u1 plus v1, u2 plus v2. So that's all the same. Then the next thing to discuss is multiplication. Multiplication is a little bit more involved because there are different types of multiplication that can occur with scalars, vectors, and matrices. So they're all essentially, all but one, are essentially matrix multiplication. However, things look a little bit different if it's vectors and so on. So let's start with the easiest case, and that is if we have a scalar times a matrix. So just a scalar C times a matrix A, and it's exactly what you would think. You just multiply C times each of the elements of A. Nothing different than what you'd expect. Same thing for a vector, K times the vector U, just K times each of the elements of U. Now, the main one is when you have a matrix times a matrix, so matrix multiplication. So if I have two matrices A and B, and I want to multiply them together, I first have to check to see if they actually can be multiplied. The sizes and shapes of them have to be such that that is possible. So let me walk us through that. So A and B are two matrices. They do not have to be square. However, they do have to be such that the following rule holds. So I have A, which let's say is M by R. So M rows and R columns. And then B, which is R by N. So R rows and N columns. You have to look at these two inner dimensions, and those have to be the same. So the number of columns of A and the number of rows of B have to be the same in order for matrix multiplication to work. Then the resulting matrix, when you take the product, is M by N, which are the outer dimensions. So M by N. So these two have to be the same. If they are, then you can do the matrix multiplication, and the end result is the outer dimensions M by N. Now, what this clearly implies, which is true, is that the order matters. So obviously with scalars, the order doesn't matter. I can multiply 3 times 4 and 4 times 3, of course, I get the same thing. So that we say that they're commutative. But with matrices, they are not commutative. So the order does matter. So we will talk about pre-multiplication, post-multiplication in order to clearly indicate the order of the multiplication of the matrices. So in this case, it's A times B, and B times A is not the same. In fact, If M, R, and N are different numbers, then B times A doesn't even exist, because then the inner dimensions would be M and N, and they don't match. Okay, so we have to watch out for the ordering when we're multiplying matrices together. So here's how it looks for that case A times B, where the inner dimensions are match, and then the final result is M by N. So the resulting matrix, we'll call it C, would be M by N, and that's down here. Now this is very tedious, and this is why we love to have computers do matrix multiplication for us. So the C11 element comes from the first row of A and the first column of B. And what you do is you take the first element of the first row, multiply it times the first element of the first column. So that's A11 times B11, add A12 times B21, plus A13 times B31, and all the way through. And so these are the same size. So A1R times BR1. So the product of all of these with all of these and add them up, that gives you C11, the 1, element of the product. For C12, that's the first row and the second column. So first row, second column. And you just do the same thing. And then you just do that all the way through. So a general Cij, so that's the ith row and the jth column, is the product of all these A's and B's. All the A's on the ith row and the B's on the jth column. Jth column? That sounds strange. So it's this sum. So again, very tedious for matrices any larger than 3 by 3, 4 by 4 kinds of sizes. That brings us to the inner product, or sometimes we call it the dot product, or some people call it the scalar product. I'll usually call it the inner or the dot product. So this is matrix multiplication, but applied to vectors. So when you have a vector times a vector, there's two different ways to do it. The matrix multiplication way is the inner or dot product. The notation we usually use is either U comma V in these angle brackets or U dot V. Okay, it's the usual notation. In terms of vector matrix products, this is actually U transpose times V. So U transpose times V. U transpose takes the column vector for U and lays it down. And then V is the column vector V. So if you look at the sizes, then this is 1 by 3, 1 row, 3 columns. This is 3 by 1, 3 rows, 1 column. The inner dimensions are the same, those are 3. So I can do the matrix multiplication. And the outer dimensions are 1. So I end up with a 1 by 1 matrix, which of course is a scalar. And that is just U1 times V1 plus U2 times V2 plus U3 times V3. Add those up, you just get a number, it's a scalar. That is the inner or dot product of two vectors. And in this case, the order does not matter. So U dot V and V dot U are the same. And you can check that easily. So using dot product or inner product operations, we can revisit the matrix multiplication. So what this equation is saying is to get the Cij element in the product, you take the ith row and the jth column and you take their inner product. So inner product of this with the inner product of this vector with this vector, and we get this scalar result. All right, so the dot product is a special case of matrix multiplication, but matrix multiplication involves doing a whole bunch of dot products. You have to do a dot product for every single element in C. Now there is one other type of multiplication that only applies to vectors, and it only applies to 2D and 3D vectors, and that's the cross product. There is no matrix equivalent of the cross product, and the cross product does not exist for larger than 3-dimensional vectors. So this is something we use in mechanics all the time. We use it in statics and physics for things like moments and anything twisting, torsion, moments, and those sorts of things. So this is called the cross product because in the notation we use a cross, like so, to indicate it. So let's say that we have two vectors u and v, again 3-dimensional. Then the cross product of u with v, we write down this determinant. I, j, k are the unit vectors in the x, y, z direction. Then we have the u elements and then the v elements. And then hopefully remember how this goes. For the I component, you take the determinant of these two. So u2 times v3 minus u3 times v2. That's the coefficient of I. The coefficient of j, get rid of these. And then you have this and this together, take the determinant of that. Remember, it's a minus, so minus that determinant. And then similarly for k, get rid of these, take this little determinant, and that's the coefficient of k. So that's the typical cross product like we've seen in physics and so forth. Then the direction, so this is actually a vector now. Remember, the dot product or inner product is a scalar, whereas the cross product is a vector. So remember when you take moments, right-hand rule. So if you have a position vector and a force vector, you take their cross product, and the magnitude gives you the magnitude of the moment that that force has with that position vector, and the direction, which is always perpendicular to that plane, that direction is the direction of w, okay, the cross product, and that's always perpendicular according to the right-hand rule. You know, where your fingers are sweeping from one vector, in this case u to v, and that gives you the direction of the resulting cross product, such as a moment, for example. Okay, so matrix multiplication is a little bit more complicated, different versions of it, two versions for vector and vector multiplication. One is the dot product, one is the cross product. So we have to keep all those straight. Now here's some rules. So these are some mathy rules just to make sure we know how to do these operations. Most of them are exactly what you would expect from scalar algebra, what we learned for scalar algebra, except for the fact that we have to keep the order of the matrices the same. So if I have A, B, C, I could first multiply B times C and then pre-multiply A. That will give me the same result if I first multiply A times B and then post-multiply C. The important thing is I keep the order the same. So ABC, ABC. Whether I do BC first or AB first doesn't matter. I just have to be sure that the order is maintained. Same thing here. So this is the associative property of matrices, right? I can associate different matrices with each other. The distributive property says if I have A times the quantity B plus C, if I distribute the A, that's A times B plus A times C. But you can't flip the order. So if the A is out front here, I can't have B times A plus C times A. I have to keep the AB, AC order intact. Same thing if the A is at the end, I can still distribute it, but now it is B times A plus C times A. Remember last time we talked about the identity matrix? It's kind of like 1. It's the matrix version of 1. So if I multiply a matrix times the identity matrix, I just get back the matrix. And in this case, the order doesn't matter. A times I and I times A are the same. They're both just the original matrix A. A to the power n, just like for scalars, it's the product of A times A times A times A, n times. but now it's matrix multiplication. I have to multiply A times A, and then that times A, and then that result times A, and that result times A, n times. So extremely tedious, but it's exactly what you would think. A to the power n times A to the power m, just like for scalars, you add the exponents. So it's A to the power n plus m. Likewise, if I have A to the n and then that to the mth power, that's A to the n times m. Again, just like for scalars. This one's a little harder to see, but it turns out it's the same as for scalars. A to the power 0, just like a number to the power 0 is 1, a matrix to the power 0 is I, which again is just the matrix version of 1. So what you'll see is all of the scalar arithmetic versions of these follow directly from these more general cases. So if A and B were simply scalar numbers, not matrices, all of these hold if I was 1, all of these hold. And so in other words, the arithmetic and algebra that we learn for scalars is just a special case of this for matrices. All right, let's talk about applications. I've said this before, but I'm going to emphasize it over and over again. The course title is Computational Mechanics. This is not numerical methods. This is not math for the sake of math and computers for the sake of computers. This is computational mechanics. We want to solve real problems of interest to us as engineers. So I'm going to emphasize applications a lot. And I understand that when I bring applications in, as I do here, my first example is going to be an electrical circuits example. Now, not all of us are up on our Kirchhoff's laws and Ohm's law and so forth. I understand that. Then I'm going to do a truss example. And some of us have forgotten some of our MMAE 200 statics. I get that. But I want to emphasize over and over again the connection between what we're doing and applications. So when I do these examples, don't get caught up in the details of the circuit analysis or the statics from which we get the equations. What I want you to see in all these examples is how they all lead to a system of algebraic equations to solve. That's what I want you to see. So we're engineers, so we have a physical question. The physical question will be, what are the currents in the different pieces of a parallel electric circuit? The physical question will be, what are the forces in the members of a truss? The physical question will be, what is the velocity of a fluid passing between two plates? So we're always asking a physical question as engineers. But that physical question boils down to solving a mathematical problem. So you're going to hear me say that all the time throughout the semester. What's the physical question? And what is the mathematical way to answer that physical question? And in doing so, I want you to see the beautiful marriage between the physics and the math, the physics and, in this case, the numerics as well. So all of these lead to a system of equations. A u equals b. A is a matrix, n by n or m by n. U is going to be the solution vector that we're looking for. Those will be the forces in the truss, the currents in the electrical circuit, and so on, the velocities in our fluids problem. And then the B is a known right-hand side vector. So there's going to be this common mathematical structure to every problem. But what A represents, what U represents, what B represents would be different depending on each particular application. So for example, we could look at the forces in a static system. Static just simply means not moving. It's static, it's not moving. A system of discrete objects. They could be masses in a spring mass system. They could be the members of a truss. It doesn't matter. Just it's a static system that's not moving, not changing with time. If we're doing a parallel electrical circuits problem that only contains voltage sources and resistors, if we have inductors and other things, then it actually becomes a differential equation problem, not a linear algebraic equation problem. But if we have just voltage sources and resistors, then when we analyze our electrical circuit, we'll do an example in a moment, we end up with a system of linear algebraic equations. CAD, or computer graphics. So when you guys play your computer games, every time you change the orientation as you look around your whatever in your game, there's a whole bunch of, the computer's doing a whole bunch of matrix vector multiplications in order to change the view of the graphics that you're seeing in front of you on the screen. So that's all linear algebra. All of that is linear algebra. So same thing in CAD, computer-aided design. So you create a three-dimensional design, and then you can rotate it, you can change the orientation, you can make it bigger, you can make it smaller. And every operation that you do when you're doing that is a coordinate transformation, which is a matrix multiplication system of equations. Probably the most important example that we'll look at is when we apply numerical methods. So again, the objective is I want to solve a physical problem. I want to know what's the solution to this physical problem. In some cases, like these first two, which we'll look at in a moment, the system of equations results directly from applying the physical principles. So we have our physical system, we apply the physical principles, we get a system of linear algebra equations to solve. Great, we're good to go. In some cases, I start with my physical system, I apply the physical principles, and I don't get a linear system of equations yet, I get something else. Usually it's a differential equation, might be ordinary, might be partial, but I usually get a differential equation that I now need to solve. Sometimes I can solve it analytically, but most of the time I can't. So I have to do it numerically and approximately. So I'll introduce now how we'll do that. At the end of the semester, we'll focus on that in much more detail, but I'll just give you a kind of a brief introduction to that today, maybe a little bit more detail than you want, but nevertheless enough so you can kind of see where this is going. But in all cases, the end result is some linear system of algebraic equations that we need to solve. That's where we're working towards. All right, so let's do a simple electric circuits example. We have three parallel circuits. So therefore we have three currents, I1, I2, and I3 that we need to determine. I have voltage sources, I have resistors, and I want to determine these three currents given the voltage sources as well as the resistors. So the relevant physical principles, again, don't get bogged down in the details. The point of this is not to remind you or teach you how to analyze parallel electric circuits. So don't worry about the details, just focus on the big picture. But I have a real problem I now want to solve, and I'm going to apply the appropriate physical principles. And then as you'll see, that leads directly to a system of linear algebraic equations for, in this case, the currents. So first of all, we have Ohm's law, V equals IR. So the voltage drop across the resistor is equal to the current through the resistor times the resistance of the resistor. And then we also have Kirchhoff's laws. So there's two Kirchhoff's laws. The first one says that whenever you have a juncture, like right here, you have a juncture, the sum of the currents coming in and out all have to match. So you can't have current magically appearing or disappearing anywhere in the circuit. So what's coming in here, here, and here all have to add up so that whatever current's coming into that joint has to be going out of that joint or juncture. So that's the first one. The second one says that the voltage drops around each closed circuit must be 0. So I have a voltage rise because I have a voltage source. Then there's a voltage drop here, another voltage drop here, and another voltage drop here as I go around this first part of the circuit, first parallel part of the circuit. Okay, so all the voltages plus, minus, minus, minus all have to add up to 0. Okay, so that's a physical law that has to be adhered to. So if we take that second Kirchhoff's law and apply it to each of our three parallel circuits, 1, 2, and 3, you'll get 3 equations. So loop 1, loop 2, loop 3. So let's just walk through loop 1. So I have an 8-volt source. So that's a +8. Then I continue on, and then I have a 12-ohm resistor. So that's -12 times I1. Again, current times resistance. Then I continue around, and I have an 8-ohm resistor. So -8 times that current. So -8 times, now this is I1 minus I3, because I have I1 going through here, and I also have I3 going through here. And they're in opposite directions, so I have to remember to get the signs right. Again, don't worry about those details. That's not the point here. And then for this one, similarly, I have I1 going to the left, I2 going to the right. So I have -10 times I1 minus I2. And that all has to sum to 0. Then you do the same thing for loop 2, same thing for loop 3. Now look what happens. If I take and simplify this first equation, you'll notice I have an I1 here, an I1 here, and an I1 here. So if I simplify this, gather all the I1 terms together, all the I2 terms together, and all the I3 terms together, I get 30 I1 minus 10 I2 minus 8 I3 is equal to 8. That's just simplifying that first equation. Same thing for the second loop. I have this equation. I combine all the I1 stuff, all the I2 stuff, and then all the I3 stuff, and I get this, -10 I1 plus 16 I2 minus 6 I3 is equal to 4. Same thing for the third equation, I get this. So I have 3 equations for 3 unknowns, I1, I2, I3, the currents in each of the 3 loops. If I write this in matrix form, so this is an equivalent mathematical way to write these 3 equations for 3 unknowns, I take the coefficients of the I1s, those become the first column of A. The coefficients of the I2s become the second column of A. And then the coefficients of the I3s become the third column of A. Now, how do I know that? Because if I unwind this system of equations, and if I do the matrix multiplication, this is 3 by 3. This is 3 by 1. So the result is 3 by 1. So that all makes sense. Not only that, but if I do the matrix multiplication, this 3 by 3 matrix times this 3 by 1 vector, I will get this 3 by 1 vector. First row, 30 times I1, 30 I1, minus 10 times I2, minus 10 times I2, minus 8 times I3, minus 8 times I3 is equal to 8. Everybody see that? So that's just straight matrix multiplication to go backwards from this to this. All right, and you can obviously see this is the B, 8, 4, 6, 8, 4, 6. So now this is our A, U is equal to B. 3 by 3 system of equations for our 3 unknown currents. We solve it. We'll worry about how to solve it next time. But the way we would solve, however we end up solving it, we get the currents that satisfy each of these 3 equations. And this is an important thing to remember. This is an important thing to understand. When we have these system of equations, the I1, 2, 3 solutions that we get have to satisfy all 3 of these equations. So there are situations where there is only one such solution. We call it a unique solution because there's only one. In some cases, there might be no solution. This is mathematically, not physically. Or there might be an infinity of solutions. Physically, because I can go to Home Depot and I can buy these voltage sources and I can buy these resistors and I can set up this current in this circuit in my basement, I know it has a unique solution. So mathematically, I expect to get a unique solution from this, and indeed you will. And you'll see that in the first problems that you'll do that problem, you'll solve it. If it's mathematically such that you don't get a solution or you get an infinity of solutions, that has to make sense physically as well. So most of the time, because we're solving physical problems, most of the time we will be looking for unique solutions. And we'll actually demand that we have a unique solution. All right, and that is the case here. Okay, now as I said, if I add in capacitors and inductors and other things other than just resistors and voltage sources, I will actually get systems of differential equations, ordinary differential equations, rather than linear algebraic equations. So we'll see that later in the semester. All right, so that's a circuits example. Ask a physical question: what are the currents in each of the parallel circuits? Mathematically, that boils down to solving a 3x3 system of algebraic equations. Second example, frame structures. So you would have done this in a class like MMAE 200 statics. So here we have a truss, 1, 2, 3, 4, 5, 6, 7 members in the truss. So there are 7 unknown forces that we are looking for. And you remember how to analyze these. So the main principle is that the sum of the forces as well as the moments both have to sum to 0. This is a static structure. It's not moving. So therefore, for a static structure, the moments all have to sum to 0. Otherwise, the thing would be rotating. It's not, so they have to sum to 0. And the forces all have to sum to 0. Otherwise, it would be moving. So we can apply those principles, 0 forces, 0 moments, to individual pieces of the truss or the entire truss as a whole. So the way you analyze these to begin with is you have these reaction forces. So I have my truss, fine. You'll notice I have a 3 Newton force down at C here in the middle. So I need to get the resultant forces here and here on this at the supports. So the way you do that is you first apply some of the moments and some of the forces to the entire structure. We'll do that in a moment. And then, in a little bit, and then once we have R1 and R2, then we want to find F1, F2, F3, F4, F5, F6, F7. And to find those, we have to analyze the truss joint by joint, drawing free body diagrams and doing the sum of the forces for each of the 5 joints. Okay, so let's just get started. I won't go through all 5 joints, but let's just get our feet wet and remind us how this goes. Now, all of these members are of length L. They're all the same length. So these are all equilateral triangles, and all of these angles everywhere are all pi over 3, just to keep things simple, all right? So they're all pi over 3, the lengths are L. So first, we start with some of the forces and some of the moments for the entire structure. So if I sum the vertical forces, I have R1 up, that's the reaction force at the left support, plus R2, positive up at the right support, and then minus 3, that's the force down in the middle, and those have to sum to 0. Now I can probably guess from symmetry that half of the force is going to go to R1, the other half is going to go to R2. However, I don't want to assume that. So what you do is you then sum the moments, and you can pick any point you want. So I'm going to sum around A, sum around this joint A here at the left. So I have a moment from the 3 Newton force down, and I have a moment from the R2 force up. This one has a moment arm of L. This one has a moment arm of 2L. So I do that, and I have 2L R2 minus 3L is equal to 0. So those 2 equations together, I can determine exactly what I would expect, is that half of the 3 Newton force is handled by the R1 support, and the other half is taken care of by the R2 support. All right, so that's fine, the basic statics. So once I apply some of the forces and moments to to the entire structure, I can then apply them to each individual joint. So the way we do this is we draw free body diagrams for each of the joints. I'm just going to do 2. I'll do A. So let's take this A here. So I have R1 up. I have a force F2, and I have a force F1, and then pi over 3 is the angle between them. So remember, when you do free body diagrams, you extract out the piece that you're doing a free body diagram for, and everything that gets cut away gets replaced by its associated force. So in this case, you're cutting these two members, so you have to replace them with the force in those two members, F1 and F2. And I don't know, is F1 in tension or compression? I don't know. Is F2 in tension or compression? I don't know. You just let the math sort that out for you. So this is on the next slide, but if you do the sum of the forces in the X direction and then the Y direction at this joint A, you get these two equations. So let's look at the first one. Sum of the forces in the X or horizontal direction. I have F2 to the right, so that's plus F2, and then F1 off on this pi by 3 angle. So that's F1 cosine of pi over 3, and those have to sum to 0. In the Y direction, F2 doesn't come in, R1 does, and the vertical component of F1 does. So that is R1 plus F1 sine pi over 3 has to sum to 0. So remember this from 200, it's tedious. So you do that, you have two equations for each joint. Sum of the forces in X, sum of the forces in Y, sum of the forces in X around B, sum of the forces Y, B, and then C, and then D, then E. So there are 5 joints, 5 times 2. I only need my fingers, I don't need my toes, is 10. So I end up with 10 equations. How many unknowns do I have? Anybody? How many unknowns do I have that I'm looking for? Seven, right. 1, 2, 3, 4, 5, 6, 7. Now you wanted to say 10, because if I have 10 equations, then I can have 10 unknowns, right? And you want them to match. For truss problems, they actually never match. So I actually have 7 unknowns, but 10 equations. Mathematically, we say that the system of equations is overdetermined. I have more equations than necessary to get a unique solution. In order to have a unique solution, therefore, that means that some of the equations are really just linear combinations of the other equations, which means I can write, so let's just say, for example, the last equation, which whatever it happens to be, here's the whole system. This last equation, I can write as some linear combination. So something times one of the equations plus something times one of the other equations. And therefore, it's actually not, it's not contributing anything new to the information contained within the system of equations. It's redundant. So 3 of the equations have to be redundant in that way. If that's true, then I have 7 unknowns and really only 7 unique equations, and therefore I get a unique solution. That's what happens in these truss problems. So I'm getting a little bit ahead of myself. So again, I have these 10 equations, 5 times 2, and here they are. I've written them all out. So remembering that cosine pi over 3 is a half, sine pi over 3 is root 3 over 2. This is what you get. So for the first equation, it's F1, and the coefficient is cosine pi over 3, but cosine pi over 3 is a half. So that's this 1/2 right here, times F1. And then the second element, that's the 1 coefficient here, times F2. And you'll notice in the first equation, there's no F3, there's no F4, there's no F5, 6, or 7. So those are all 0. So it's 1/2 times F1 plus 1 times F2 plus 0 times F3 plus 0 times F4 plus 0 times F5 plus 0 times F6 plus 0 times F7. And that is equal to 0, the right-hand side of my equation. Yeah. Oh yeah, sorry. Yeah, I turned on the chat. Let me answer this question. So, Dr. Castle, when doing homework, will you ask us to solve the problems on paper and then on Python MATLAB? So the answer to that is yes and yes. So some problems on the homeworks will be paper only, work it out by hand. Some will be primarily Python or MATLAB, and some will be a combination of the two. Set it up on paper, solve it using software. So you'll get all of those, Diego. Every possible combination and permutation that I can think of, you will be doing in the problem set. So you get lots of practice with both. Okay, so that's the idea. And you do that for all 10 equations, and these are the equations that you get. Now, the things to notice about this system of equations, first of all, I've already said there are 7 unknowns, but there are actually 10 equations. So we discussed that. But notice the information that's contained in A and the information that's contained in B. What is the information contained in B, the right-hand side vector? Yeah, the reactions, and that's it, plus the external force. Yeah, so this is all external forces. Now the F's, those are the internal forces. That's what we're looking for. So F1 through F7, those are the forces within each member of the truss. That's what we're looking for. And what is this information here? So the matrix A itself, what does the matrix A contain? What information does it contain? Or what influences A? That's another way to think about it. Anybody? Yeah, so it's got distances in it, and what else? Distances and look at all the numbers. Whoops. Look at all the numbers. They're 1/2s and √3s over 2s and 1s. Angles. So distances and angles. That's the geometry. So this, the matrix A, has all the, whoops. What did I do? How did I get that giant thing? Oh, there we go. Has all the information about the geometry. And this is always how these structures problems go, whether it's trusses or any other kind of structure. The information that goes into the coefficient matrix all has to do with the geometry. So lengths, angles, and how the different pieces are associated with each other. So in this case, for example, the fact that F1, F3, and F4 all are joined at B, that gets built into the matrix A. So that's all geometry, linkages, distances, and angles. External forces all go into B. So what that says is, if I'm analyzing a structure, such as in this case, a truss, I can take the same truss and I can change the external forces simply by changing B. A stays the same because the geometry is the same. So I could move my 3 Newton force, or I could change its value. I could move it to another node, or I could change the value itself. And that, of course, will affect the reaction forces. But all those changes only affect the B. What that means is there are a number of methods for solving these systems of equations, which if you only change B, you only have to do a little bit of extra work. So all of the work, most of the work, almost all the work comes from dealing with A. And as long as A doesn't change, you don't have to redo that work. If only B changes, then that's just a little bit extra piece. And we'll see that, we'll come back to that. So just remember that. A stays the same, B changes. In certain methods, we can take advantage of that. But again, the point is, why is that the case here? It's all because of the physics. I didn't impose that. I didn't assume that. I didn't do any tricks to make that happen. That all followed naturally from the physics of the problem. And that's always going to be true. So watch out for that. You're going to hear me emphasize this over and over and over again. Even with masks on, I should be able to see your eyes rolling like this. Oh, he's going to emphasize that again. Oh, I should hear an audible groan and see your eyes rolling, because I'm going to emphasize that so very much. You're going to get sick of hearing me say it. Right. got the angles, good. Okay. So I said these things, I said all that. Yep. Let's look at another statics problem. All right, so again, statics, nothing's moving. Let's look at a static spring mass system. So here it is. It's a very simple problem. I'm going to have one spring with a mass. That'll be M1. And then another spring with a mass M2. And then, of course, we'll have acceleration due to gravity. These forces, so F1, it's a linear spring. So the force in a linear spring is what? Remember? What's the force in a linear spring? So K, the spring constant, times the elongation, right? So if I say this is X1 and this is X2 position, then this one's going to be K1 times X1. So the spring constant for that spring times the elongation of that spring, which is X1. Same thing for the second one. F2 will be its spring constant K2 times X2 minus X1. So the elongation of the second spring is the difference between those two. Again, don't get caught up in the details. I just want you to see, starting with physical problems, asking physical questions that they lead to a mathematical problem that in this case just happens to be an AU equals B. Don't get caught up in signs. Why is that positive? Why is that negative? Okay, don't worry about those details. All right, so how do we analyze this? Well, we analyze it the same way. We do free body diagrams. So in FBD, let's call this 1 and 2. So each of the two masses. So for mass 1, and then we'll do a free body diagram for mass 2. Okay, so for 1, once again, you take the thing, in this case, that's the mass, and you isolate it. And in isolating it, you replace all of the things you cut away with their associated forces. So pulling up is going to be this force F1, which is K1 X1. Pulling down is going to be the force on the other, from the other spring, which is K2 X2 minus X1. And also the mass, M1G. So the weight of that mass, M1 times G. Okay, and then we'll sum the forces. Let's do free body diagram 2. So free body diagram 2 just has two forces. Up, we have K2, X2 minus X1, the force in the lower spring, and then also M2G, the weight of the mass 2. And then we sum the forces. So the sum of the forces for 1, sum those to 0, and then we'll sum the forces for free body diagram 2, sum those to 0, and you'll see what we get. So for the free body diagram number 1, for the top mass M1, we have K1 X1, that's up, so it's plus, minus K2 times X2 minus X1, minus because it's down, minus M1G, and that has to sum to 0. Static, not moving, sum of the forces is equal to 0. Similarly, for free body diagram 2, we have the force up is K2 X2 minus X1, and then minus M2G, because that's down, and that has to sum to 0. So the way we normally write these equations, just like I did for the circuits problem, just like I did for the truss problem, we move the unknowns to the left-hand side and the knowns to the right. So I know M and G, because I know what planet I'm on, and I know what the masses I bought at Home Depot. So I move those to the right. I don't know the X's, so I leave those on the left. So if I simplify these, So the first one, I have all the stuff times x1, which is k1 plus k2 times x1, and then minus k2 times x2, all the stuff times x2. Move all the stuff I know to the right. That's m1g. Second equation, all the stuff times x1, that's minus k2 x1 and plus k2 x2 is equal to m2g. So once again, I asked a physical question. I want to know, what are the locations of these two masses given their masses, as well as the forces in the spring above and below. In order to solve for x1 and x2, those positions, I have to solve these two equations for these two unknowns. And it's a matrix problem. I didn't leave enough space to write it, but I would have the k's as the coefficient matrix, the A matrix. I'd have the x1, x2. Oops, I forgot a 1 here. I'd have the x1 and x2 are the solution. That's the solution vector I'm looking for. And then the right-hand side vector is the masses times the accelerations due to gravity. So once again, what physical information about the problem goes into A? Anybody? What physical information goes into the coefficient matrix A? Yeah, the spring constant values, as which also includes the linkages between the 1 and the 2 masses. So similar to the truss problem, it's information about the system, the interconnectedness of the system, and the spring constants. Often people will call this the stiffness matrix because it involves the K's. So that's the stiffness of the system. The solution vector we're looking for, x1 and x2, that's these positions, the positions of the two masses as they hang down due to their weights. And then the right-hand side are the weights, m1 times g, m2 times g. So again, each piece, A, U, and B, has some physical meaning. Depending on the physical problem, the physical meaning is different. However, mathematically, it's just a coefficient matrix A that I know times a vector of solutions that I'm looking for is equal to a vector of values that I know. A and B I know, and I'm looking for U, or in this case, X. Turns out this is actually a tridiagonal system. It's hard to see because I only have 2 members. If I had more, 2 masses, if I had more masses, you would see more clearly this is tridiagonal. So remember, tridiagonal has non-zero elements down the main diagonal, the first upper or super diagonal, the first lower or subdiagonal, and everything else is zeros. So it has a structure to it. It has a very specific structure, which we can take advantage of when we try to solve this. Yep, K's are constants, right? All right, so those are cases where the discretization are natural for the system itself. So the springs and masses are discrete objects. I go to Home Depot and I go to the spring aisle and I get my 2 springs. I go to the mass aisle and I get my 2 masses. They're discrete objects, they're different. So the discretization of the system is natural. It comes directly from the nature of the system itself, just like the truss. It's made up of 7 members interconnected in a specific way. So I have discrete elements of the structure such that that discretization, which is the process of breaking up a complicated problem into little pieces, in the truss and the circuits example and the static spring mass example, that structure, the discreteness of the structure is natural to the system. Does that make sense? That's the point I'm trying to make. In many systems, however, the system itself is continuous. So if I think, for example, about the fluid in this room, the air in this room, so as I'm talking, there's not much because of my mask, but I'm moving fluid around because I'm talking, and the HVAC comes on and off periodically and it starts moving air around. That door is open, that door is closed, so some fluid can move in or out of that door and so on. So there's movement of air in this room. However, there's no natural discretization of the air until we get down to the level of molecules. We don't want to do that if we don't have to. So we regard the air as a continuum. The way we experience the air in this room is as a continuum. I don't feel each individual fluid particle molecule hitting my skin. I just feel the overall pressure continuously over my entire skin surface of the air acting on me, the pressure of the air acting on me. So my point here is that in these continuous systems, such as in solid mechanics, fluid mechanics, heat transfer, the discretization does not come naturally from the system itself. Instead, it's going to come from how we simplify or approximate that system. So in order to make the solving of the air problem in this room tractable, doable, I will want to divide it up into little chunks. So rather than an infinity of air molecules throughout this three-dimensional space, I'm going to chunk it up into little pieces. So maybe I have thousands, or maybe I have millions of pieces. All right. But the point is, I'm imposing through my approximation, I'm imposing that discretization rather than the discretization arising naturally from the system itself. So that's the fundamental difference between discrete and continuous problems. Now, how I solve the air movement problem, I have to look at fluid mechanics. So that's 313. Most of you have not had MMAE 313. You're not taking it yet. Some of you might be. But I'll show you one simple example that you'll do in that class. It's called Couette flow. You have two flat surfaces that are parallel, like this, and you have a fluid in between them. All right, so it's air, water, doesn't matter. And then the upper surface, we're going to move with the constant velocity, capital U. And I want to know what's the velocity distribution of the fluid in between the two flat surfaces. So it seems like a very simple problem. So the gap height will be h. Again, the upper surface velocity will be capital U. And I'm looking for U as a function of y. So I'm looking for what is the U distribution at every point vertically between that gap. So U as a function of y. How many values of y are there? There's an infinity of them. So how many u's are there? There's an infinity of them. So again, the discretization is going to be imposed by me. It's not natural to the problem itself. Now we would start with the governing equation. So when you do take fluid mechanics, you would find that that's the Navier-Stokes equations. We would make the appropriate assumptions and simplifications for this particular flow. And that leads to this relatively simple differential equation. D squared U dy squared is equal to a constant. And that constant involves the viscosity of the fluid mu. So that's how thick it is. And dP dx, which is the pressure gradient. So we're going to allow for a pressure change from left to right in the direction of the motion of the fluid. So the fluid is moving, first of all, because this upper surface is moving with some velocity. It's also moving because it's being pushed by a pressure gradient. So if the pressure is higher here than it is here, it's going to push it from left to right. All right, so those two things together, the viscosity and the pressure gradient, we're going to assume is a constant. So we just have d squared u dy squared is equal to a constant. Now, of course, you're going to say, well, I can solve that. I don't even need a differential equations class to solve that. I just integrate that constant twice, put in the boundary conditions, which I'll give in a second, and we're done. All right. So, but we're going to pretend that the equation is actually more complicated so that I can't solve it exactly. I need to solve it approximately. I need to solve it in a numerical fashion. Here are the boundary conditions. Basically, they say it's called the no slip condition. They say that the velocity at the surface, the velocity of the fluid at the surface, is the same as the velocity of the surface. So the fluid adjacent to the bottom boundary at y is equal to 0 has 0 velocity. The fluid adjacent to the top surface at y is equal to h has a velocity capital U. So the fluid is moving at the same speed as the adjoining surface. That's called the no slip condition. There's no slip between the surface and the fluid directly at the surface. They go at the same speed. All right, so we have a mathematically consistent and complete problem. We have a second order differential equation, and we have two boundary conditions to solve. We call this a boundary value problem. And again, I could solve it in 2 lines, integrate twice, put in the boundary conditions. Okay, maybe it'll take me 3 and we're done. But we're gonna pretend like the equation's more complicated. So that is essentially the first step in what I call the numerical solution procedure. Here it is. This is just a preview. We'll talk about this more later in the semester, but just to give you an idea, and this is a good framework, kind of schematic to have in your mind as we go through these problems. We start with the physical system. Again, we're engineers. We want to solve physical problems. We want to understand how physical reality behaves. So that's always our starting point. Then we apply physical laws and models. So physical laws are things like conservation of mass, conservation of momentum, conservation of energy. Models are things like maybe I'll use the ideal gas law. Maybe I'll assume that there's no friction. Maybe I'll assume that it's 2-dimensional or 1-dimensional. So those all go into step 1, which is to translate the reality into the governing equations for that physics. That we call the mathematical model. So it's a mathematical model of the physical situation. In this case, that's this. The equation plus the boundary conditions, that is the mathematical model. If we can, we solve it analytically. And in many of our other classes, that's what we do. So we start with physical system, apply the appropriate physical laws, we get the mathematical governing equations, and we solve the problems analytically when we can. This class is for when we can't. And of course, in real engineering problems, not the little toy problems we give you in textbooks, but in real engineering problems, we can almost never get an analytical solution. So instead, we're going to solve it numerically. That brings in the second step, which is discretization. So you've heard me talk about discrete versus continuous. So these are continuous problems. These are continuous differential equations at this stage in the mathematical model. Then we discretize it. We impose a discretization on that continuous system, and that will lead to a system of algebraic equations, which we then solve somehow. That's step 3 to get our numerical solution. So again, we'll come back to this later in the semester when we're talking about these kinds of physical problems, but just have this general image in your mind. So now when I go back, here's my physical system. That's reality, right? Physical question is, what's the flow between 2 parallel surfaces? When I apply the physical laws and make whatever appropriate assumptions, I get my mathematical model. That's step 1. Going from this to this, step 1. Okay. Now I want to just briefly, we'll do this in more detail later in the semester, but just briefly think about step 2. How do I turn this system of governing equations, or this continuous, smooth U as a function of Y solution and the corresponding equation? How do I turn that into a system of algebraic equations, AU equals B, that I can then solve for U, which are the velocities? Okay, that's the question I want to look at. All right, so let's lay it down. So let's take our domain, which starts at y is equal to 0 on the left. I've taken the bottom, put on the left. I just laid it down, so it takes up less space. And the top is at y is equal to h, all right? We're going to discretize our continuous domain into equally spaced intervals, okay? So I know what h is. That's the physical dimension, distance between the 2 plates. I'm going to decide on I. Maybe it's 10, maybe it's 20, maybe it's 100, maybe it's 1,000, I don't know. But it's the number of little pieces of the fluid. If I do it vertically, it's the number of little pieces that I'm going to discretize my continuous fluid into. For this problem, 10 is sufficient. For a more complicated problem, I might need 50 or 100. For a really complicated problem, I might need thousands or maybe even millions. For a simple problem like this, probably 10, 20 is more than enough. So generically, just look at these 3 points. There's the point I, which could be 1, 2, 3, 4, all the way up to capital I plus 1. We have the point to the right, little I plus 1, the point to the left, little I minus 1. I'm approximating the equation right here at yi, okay? And that approximation is going to involve the values above and below, or to the right and to the left. So I'm going to first motivate this just from the definition of the derivative from calculus class. Later in the semester, we'll motivate this and we'll formally derive it using Taylor series. Either way, it's very simple and you get the same result. But I'm just going to motivate it using the definition of the derivative because it's something that's somewhat familiar to us, at least I hope so. So this defines what's called the grid or the mesh. Okay, these intervals, that is the grid or the mesh. We use those two terms interchangeably, synonymously. This is what's called a finite difference method because I'm going to take differences, I'm going to subtract over finite lengths, which are these little delta y's. This is just rise over run. So it's a derivative. I want to approximate du dy at a generic point in my domain at y is equal to yi. So I have a first derivative du dy, and I'm going to approximate it using the definition of the derivative. And you say, wait a second, the definition of derivative, that's not an approximation. I know, it's not, but give me a second. So, excuse me. The definition of the derivative is if I take u at yi plus 1, so that's the value of u right here, minus u at yi, that's right here. If I take the difference between the values of u at these 2 points, and if I divide by the distance between them, so that's the rise over the run, if I take the limit as that distance goes to 0, so as those 2 points get closer and closer together, in that limit, that gives me the derivative du dy I'm looking for. That's just the definition of the derivative from calculus class that we all, of course, remember vividly. Now, how can I use this as an approximation? What we're going to do is instead of taking the limit as delta y goes to 0, let's just say delta y is really small, but it's not 0. So in other words, for this to go to 0, then I would have to have an infinity of points in my domain. But I only want to have 10 or 20 or 50 or 100 or whatever. So that means my delta y is going to be a finite distance. Now it'll be small, but it's not going to be 0. So if this limit goes away and I say delta y is small but not 0, then it's no longer an equal, it's now an approximation, right? So now it's an approximation. U at yi plus 1 minus u at yi over delta y, rise over run, is now an approximation for this first derivative. Now I'm going to write this a little bit of shorthand. So u evaluated at yi plus 1, I'm going to write as u sub I plus 1. So that's just shorthand for u evaluated at yi plus 1. Same thing for uyi. I'll shorthand for that will be u sub I. So this again is rise over run. We actually call this a forward difference for reasons that we'll see later in the semester. Another alternative would be the central difference. Now the forward difference comes directly from the definition of the derivative. But if I were to use a central difference, and I think in terms of rise over run, so again, let's go back to this. Rather than using these 2 points to get the derivative at this location, let's use these 2 points in order to get the derivative at this location. So if I were to do that, that's called a central difference for logical reasons. So that would be u at I plus 1 minus ui minus 1, rise over run is now 2 delta y's because it goes over 2 intervals in my grid. So this actually, it's still only an approximation for the first derivative, but it's actually better. And I don't know how much better yet, but when we use the Taylor series, we can actually prove that it's better, and we can show how much better, we can quantify how much better it is. So this is the one we're going to use. So 2.4 is an approximation for the derivative, the first derivative at a location in my domain. And I can apply this at any yi. I just take the two neighboring points, the point to the right, the point to the left, take their difference, rise, divided by the distance between them, run, and that gives me an approximation for delta y is small for the first derivative. Now, if I go back to my equation, I actually need the second derivative, not the first derivative. So what we'll do, again, don't get bogged down in the details. If the details are confusing at this point, that's understandable, and just kind of follow along with the overall idea. So what I'm going to do is recognize, okay, the second derivative is the first derivative of the first derivative, right? So d squared u dy squared is d dy of du dy. Fine. I have an approximation for du dy, and I'm now going to apply the same approximation for the outer du dy. So one way to think about that is if I apply that first derivative at a point halfway to the right, minus the point halfway to the left, and then the distance between them is now delta y. And then I apply my finite central difference approximation for this, and also for this, I get this mess right here. So this is a central difference at I plus a half. This is a central difference at I minus a half. And if I take this minus this and divide by delta y, that gives me this outer derivative. Again, don't start throwing rotten. You can throw snowballs at me, but not rotten fruit, please, or vegetables. Now, if I simplify this, so here's a ui, here's a ui, take the delta y's here and simplify things, I get this, 2.5. Notice the pattern, ui plus 1 minus 2 ui plus ui minus 1. So it's still 3 points, one to the left, one to the right, and the middle point. But now the denominator is delta y squared. So the first derivative, I have this approximation, point to the right, point to the left. And for the second derivative, I have this approximation, point to the right, point to the left, and the point itself. This is again called a central difference approximation, but now for the second derivative. So look what happens. This is what I'm looking for. This is the d squared u dy squared on the left side of my equation, right? The right side is just a constant. So now I can approximate my continuous differential equation using the right-hand side is the same. It's just a number, it's just a constant, using my finite difference approximation for the derivatives. And that's the basic idea behind these numerical methods applied to differential equations. Again, this is just a preview, just an introduction. We'll see this in much more detail, and it'll be much more clear when we look at it in full later in the semester. All right, so now if I think about this as a system of equations, right? Because I have to apply this at every point, I. So when I is equal to 1, when I is equal to 2, when I is equal to 3, at every point throughout my domain. So I'm going to get a new equation, a new algebraic equation, every time I apply that expression at a new point. The equation is going to look like this, all right? So A is just the coefficient of ui minus 1, B is the coefficient of ui, C is the coefficient of ui plus 1, and then D is the right-hand side. And you can see if I multiply through by the delta y squared, then the A and the C are just ones, coefficient, coefficient, and the B is minus 2, its coefficient, and then everything else is on the right-hand side. It all gets lumped into D, which is the constant. And then I have my boundary conditions, which we had before. And look what happens. When I apply this equation, we call this the difference equation. When I apply that equation for I is equal to 2, I get this. I is equal to 3, I get this. I is equal to 4, I get this. So I do that for every single point in my grid. So now I get a system of equations, which is linear and algebraic. You can see the pattern in the coefficients, ABC, ABC, ABC. it actually looks like this. So the A matrix, these are all zeros. Everywhere there's not a letter, those are all zeros. That's my coefficient matrix. Notice the pattern. It's tridiagonal. I like tridiagonal matrices because it turns out I can solve them very, very efficiently using a very simple algorithm, which is very, very fast. So I get a tridiagonal system, only 3 non-zero diagonals. These are the values of u, the velocity, at each of the grid points, and then the d's on the right-hand side. And again, the d's are all the stuff I know. That's related to this 1 over mu dp dx, and then I've multiplied through by the delta y squared. Again, don't worry about the details. Have I said that yet? So I get a big system of equations to now solve. Capital I, remember, that's the number of points. That determines the number of unknowns. So if I have 10 points, I now have 10 equations for 10 unknowns. If I have 100 points, I have 100 equations for 100 unknowns that I now need to solve. Okay, so we're basically done. We're out of time, but let me just finish this up. Just emphasize again, my matrix is tridiagonal. There is a particular structure to the A matrix, to the system of equations. This is typical of numerical methods. So the A matrix is not just some generic matrix. It typically has a structure. This one we actually call sparse. A sparse matrix has lots of zeros and not many that are non-zero, not many elements that are non-zero. Not only is it sparse, but it's structured. It has a very specific and very particular structure. So when we develop methods for solving these systems of equations, we can take advantage of the sparseness and the structured nature of the A matrix. So we would solve it. We would solve this tridiagonal system, and we would get the solution. So it'll look like this, and then we'll be done. So here's my lower surface. Here's my upper plate, which is moving with a velocity capital U. And in between, I have a velocity distribution that's going to look something like this. So at each point, this would be U2, and then say, I'm just going to call this U8, 9, 10. So for every y value, I have a velocity. And when I smooth them out, that gives me the velocity distribution. So the things I want you to see are, number one, can you see how I've discretized this continuous domain, which has an infinity of y's? I've discretized it into, say, 10 or 11 or 50 or 100, whatever. In this case, it would be 11, right? So I've discretized it. And then in so doing, I end up with having to solve a big system of equations in order to get the values of u at each of those discrete points. So that's the idea. In all of these cases, then, what we're seeing is physical question results in a mathematical problem to solve, which is a big system of algebraic equations. So that, of course, then leads into how do we actually solve those systems. We'll talk about that on Thursday, how to use exact methods to solve those systems. Some of these terms will be familiar to. Gauss elimination, Cramer's rule, you've probably heard of those, and we'll talk about a couple others. All right, any questions before we go? I know I went 2 minutes over. That's to make up for 2 of the 4 minutes I robbed you of on Thursday. People have been asking me for refunds. I'm serious. You guys are looking at me like I'm kidding. People are like, you robbed me of 4 minutes of the lecture. I want a refund. And they did the calculation, number of credit hours times their tuition, figured out to the minute. So I've given back 2 of the 4 minutes. I'm kidding. No one's asked for that. You guys, oh, don't get me started. Students are the one customer that wants the least for their money. If I told you right now, can you tell this gets me upset. If I told you right now that Thursday's class was canceled, you'd all be like, woohoo! What product you hope they give you less for than what you paid? You should be asking for more. Professor Castle, this is not enough. please come back after dinner and teach us more. I'm kidding. I understand how it is being a student with 5 or 6 classes, and yeah, it gets a little dicey. Okay, so anyway, I'll see you Thursday, and we'll pick it up from here, looking at how we now solve these systems of equations. So this was step 2, how we do the discretization. Now we're going to discuss step 3, which is how we solve the big system of equations. All right, so I'll see you on Thursday. Now with my rant, I've made